would start at this point, inviting on stage Eleni Triantafillou, that is a research scientist at Google DeepMind. She got her PhD from the University of Toronto, and she was advised by Raquel Ultrasan and Richard Zemmel. And the research interests are around methods that allow efficient and effective adaptation of deep neural networks to cope with distribution shifts, introduction of new concepts, and mostly I would say, given the title of this talk, removal of outdated or harmful knowledge. So thank you so much for being with us today, and please go ahead, the stage is yours.
Hello, everyone. Thanks for the introduction. Thanks for having me. Work? Can you hear me? Yes, cool. Um, Great. So I'm going to get started. I named this talk, Are We Making Progress in Machine Learning? And usually, people hate questions titles. I also fight with my co-authors on whether we should have a question as our paper title. The pushback is that if there's a question, the answer is always no. So maybe you'll see what's coming. But I want to stress different parts about unlearning that I think are challenging and that we need to make more progress on. And I'll talk about efforts so far in the community. I want to acknowledge my co-authors and colleagues. The work of ours that I will talk to happened through many conversations, and many ideas presented are not just mine. There are many people's. And I can tell you more about these awesome people later. Okay, so to kind of motivate this, what is the absolute dream? One of my dreams, and maybe of other people's in this room, is to sort of build systems that are able to do rapid adaptation. They can learn new tasks quickly, and maybe even more ambitious, the more tasks you learn, the faster you become at learning new tasks, and by leveraging forward transfer, and you learn in this kind of continual, lifelong manner. And I've studied this a lot in the past in the context of like few shots learning, maybe one step of this continual problem. How do you go from one model trained on one data set or distribution to another? And there's more complex tasks and benchmarks, like this continual learning benchmark from Razvan and Amal and other folks here as well. And another aim of the continual learning community is sometimes to avoid catastrophic forgetting. So we want to learn new things, be able to transfer to new tasks, and avoid forgetting old tasks, right? Well, I'm here today to tell you that sometimes forgetting is good and it's useful, or it's maybe even necessary. And so we will talk about in this talk about unlearning, which is a generic term. It can mean many things. Let's just say, for the purpose of this talk, unlearning refers to forgetting that is intentional and that is targeted. And we will narrow down a bit more later what we mean and how we would measure it. So let's take a step back. I said something that is maybe maybe not everyone would agree with me on, which is that forgetting is sometimes beneficial. And I think there's been a lot of study in this area for humans as well, before we start talking about networks. And many of you know this stuff better than me. I'm not a neuroscientist. So perhaps all of you have better insights on this. But I've been trying to understand a little bit some of these papers. And I think some neuroscientists are starting to think about forgetting as a good thing, because it can, promote plasticity and adaptation to new things. Richards and Franklin also said that it is the interaction between persistence and transience that allows for intelligent decision making in dynamic and noisy environments. So we actually want both of these to exist, and this has been, discussed in many talks as well. Doina and others talked as well about slow and fast learning, but also perhaps explicit forgetting is useful. Okay, but we are at a machine learning conference. So what does forgetting and remembering mean for machine learning models? Let me give you one definition here of memorization. I'll give you another later. We'll also talk about forgetting to kind of draw these parallels in neural networks. So this is a definition from Feldman's seminal paper that's called A Short Tale About a Long Tail. And we're going to call this label memorization here because there's other types of memorization that we will talk about as well. So what this is saying is that consider a data set S, which is comprised of these xi, yi tuples for many different examples I. And let's consider an individual example. Let's say the ith example. We're going to define a score, this MEM score, that tells us how much a particular learning algorithm, A, memorizes I, the ith example, if it's trained on the dataset S. And you can see that this can be written as the difference between two terms. So these two terms are telling you how often is this model, what's the probability that the model is predicting the label correctly for the ith example. And it's comparing two worlds. The first term considers models that were trained on all of the training set S. And the second term considers models that were trained excluding the example I. So what does it mean for this difference to be large? If this difference is large, it means that you're much more likely to predict the label correctly if you've trained on this example compared to training on the rest of the data sets, but excluding this example. And so what does this mean intuitively and formally? A particular learning algorithm trained on this data set would memorize this particular example if training on that particular example is necessary in order to classify it correctly. And, when would this happen? For examples that are maybe atypical, that your model would not predict correctly just by mere generalization. You have to actually include them in the training set. So the memorization literature studies examples that are mislabeled, for instance. So if it's really a cat, but you tell the model it's a dog, it's not going to learn to make that association unless you put it in the training set, because otherwise it's going to think it's a cat, hopefully, because neural networks that trained on other cats generalize. Okay, there's other notions of memorization as well. Verbatim memorization is another one that is quite popular these days. So in the context of LLMs, we notice this phenomenon that they sometimes regurgitate or directly copy things from the training set, and they can regurgitate it and output the exact same text. So Carlini et al. Formalized these definitions of model extraction here, which says that a string S is extractable if there exists a prefix that, if you condition on that prefix, the string would get generated. And then they define memorization. Oh shoot, I meant to Google how to pronounce this word before this talk so I don't embarrass myself, but I forgot to do it. So I don't know, I'm gonna try eidetic. What do you think? Yes to which? I said two things. Okay. Eidetic. Amazing. Thank you so much. So eidetic memorization, which I think is like photographic memory, like your ability to recall something after having seen it just once or a few times. So the way it's defined here, k-eidetic memorization for a string S occurs if that string is extractable, so you can find a prefix that will cause the string to be generated, and it was seen at most k times in the training set. So we can define memorization in this way as well. Okay, but there's many mysteries here. Why do neural networks memorize? It's a phenomenon that classical theory doesn't quite capture. Classic theory results would tell us that an ideal learner would kind of generalize and avoid overfitting. But then there's these findings that actually modern neural networks that are overparameterized achieve good test error, they generalize, but at the same time they memorize according to the definitions that I just showed you a second ago. And there's this insight that Carlini et al. Also formalized nicely in this paper, that although the gap between the training accuracy and the test accuracy is not too big on average for these modern networks, there exist some worst case examples that are still memorized from these models. And then there's more recent theories that suggest that memorization is actually even necessary for good generalization. But this is sort of an ongoing topic, an ongoing active research area. And to make matters maybe even more confusing, the plot thickens because not only do networks memorize, they actually also tend to forget. And so how do we explain this phenomenon? And there's many different studies that kind of have different definitions of what it means to forget. Um, a study that happened recently from Matthew Jakelski and colleagues found that examples that appear early in training tend to be or may be forgotten by the end. And what they mean here by forgotten is that the model is not influenced by these examples anymore. You could not tell that that example was used to train the model. And so they might enjoy better privacy, for instance, as we were discussing before as well in the panel. And then other works study forgetting from the perspective of, throughout training, the label might flip from being correctly classified to becoming incorrectly classified. So they define this as forgetting events, and they show that they occur in training. And certain examples are forgotten more often than others. And again, there's ongoing research as to why that is. But why does this all matter? Why am I talking about these things? These things have implications, for instance, for privacy. So if examples are memorized, they are more likely to be vulnerable to different types of attacks. The simplest privacy attack that I will talk about or mention throughout the talk is membership inference attack, or MIA. And this is a very simple attack where the adversary is trying to predict, given a trained model and an example, tries to predict if that example was used to train the model or not. And there's many variations of this attack that make different assumptions about, what is the attacker allowed to know? What does it have access to in order to try to make this type of prediction? And there's as well much more complex attacks like model inversion or data extraction, where not only do you want to predict if the example was used, but you actually want to extract training data itself. And in fact, this has been quite successful. So there's recent works that kind of demonstrate, both in the context of large language models as well as in diffusion models, that you can extract training data when prompted, or when you condition on the right prompt to generate the image. So in this talk, I am going to try to convince you that when we are thinking about continual learning, especially in the context of modern architectures that are larger and larger, we need to think about this interplay of learning and unlearning. And as our models get larger, it's more increasingly expensive to train from scratch. So we want to avoid doing retraining. We instead want to work with models that we already have and continue building on them. But as models are trained in more and more data, it's also increasingly likely that the underlying data that the model knows about has changed or needs to change for a variety of reasons, like either new data becomes available, or we want to also be able to solve newly identified tasks, or we might want to remove data, either for privacy issues that get identified, or simply because the world has changed and some data is no longer true or relevant for future tasks. Maybe there's labeling issues with the data that's only identified after the fact, or maybe poisoned data. You find out that some adversary has poisoned a subset of your data. Maybe you had a license to train in the past and you no longer have it. And there's many potential reasons why you would want to do this. And we still haven't sorted out exactly which applications can be solvable by unlearning. But there's many reasons why the underlying data changes. And so you need to update your model. And ideally, you don't want to do it by retraining from scratch. And so the dream that I showed on the first slide, updated here, we need to build lifelong systems that can learn new things and unlearn old things, or things that are no longer useful or are hampering forward transfer or are problematic or need to be removed. So unlearning is not new. It's been around for a while. Sometimes people called it other things like data deletion. In the past, it's been maybe more niche or more popular in theoretical circles, but it's recently receiving a lot of attention. So this competition that we organized last year at NeurIPS that I'll tell you about later, which was a giant undertaking and very challenging, because how to evaluate unlearning is itself a big problem, and I'll tell you about this as well. But once we launched, we got into a room with my colleagues, a virtual room, whose faces you can see here. This is the organization team for the competition. And we said, okay, guys, what do you think? How many people are we going to have What would we be happy with? What do we say? Okay, this was a success. It was worth all the efforts, all the sleepless nights. But 10 people, somebody was like very ambitious and they said, oh, maybe we're going to have 100 people participate. And turns out we had more than 1,000 teams from around the world, which was very, very exciting to see. And so I think we've made a lot of progress in at least initiating the discussions of how should we be evaluating these systems and what sort of creative ideas can we come up with and how do they compare to one another. The blog post that Fabian Pedregosa and I co-authored introducing the challenge was the third most read Google research blog post of 2023. So I think that there is now an explosion of interest and we have a lot of momentum. But the term is used very broadly, like if you read papers and you look at what sorts of, how do they motivate unlearning, what problems are they trying to solve, you're going to find a very diverse set of things in there, from the privacy issue, like improving accuracy due to like label issues or other problematic data removal, maybe compliance issues, improving forward transfer is a really interesting one, maybe very aligned with the goals of this community. Perhaps improving safety, although I have some doubts about that one. But these all sound like very, very different problems to me that span a wide range of sort of different research areas and perhaps objectives. And so really, can we really solve all these problems with the same approaches? And should we be really evaluating success for all of these using the same set of metrics? Feels a little bit odd. So what I'm going to do for the remainder of the talk is give you a specific definition, a formal definition of machine unlearning, one version of machine unlearning, the one that we've tried to solve. And so we're going to make things more concrete, at least for this talk. And then I'll tell you about this competition that I just mentioned that we ran last year, and I'll tell you what's the evaluation procedure that we came up with for it. And I'll tell you a little bit about the methods and analysis. Then I'll tell you about some recent work that we're doing on understanding what makes unlearning hard, and can we use that to inform how to build better unlearning pipelines. And I'll end with discussions, open questions, and connections with this community, perhaps opportunities for collaboration. Okay, so let me define the problem now very concretely. You have a data set D, and you train a model on it. I'm just going to refer to this model as the original model for this talk. And then after the fact, a forget set gets identified. So the forget set is a subset of the training set. It's a subset of D that we now need to remove from the model. So there actually exists a pretty easy, straightforward solution to this. You create a new training set by taking D and removing S. So this is often called the retain set, so the rest of the training data, and you just train a new model on it. This is very computationally expensive, obviously, but it's straightforward to show that this new model, the green neural network, let's call it the retrained model, does not have any influence from S, because it never saw it in the training set. But, this is expensive. And so what we would really love is if there existed this magical unlearning algorithm that, instead of having to retrain from scratch, actually starts from the original model and takes as input the forget set, and maybe the rest of the data set as well, and comes up with this orange unlearned model that looks like the retrained model. And we're going to unpack looks like in a second, but the overall goal is, can we approximate retraining from scratch, but do it much faster? By the way, I should have said this, but feel free to ask questions. Yes, there's a question. Sorry, I can't hear you.
So my question is that, is it possible some new forgetting happen in D minus S? That is.
Yes, it is. I will talk about this maybe a little bit later. It is definitely possible that there's future unlearning request in the remaining set. So like once you've unlearned this one, are you done? Well, not really, if there's future unlearning requests that come from the remainder of the data set. So this can happen sequentially. And I think we need to think about that problem as well. But for the competition and for the next like 10 slides or something, let's just say that we want to solve one of these because we don't even know how to do this right now. But ideally, yes, we want to think about the dynamics of these sequential unlearning problems. And there has been work on this already. There's been theory work that analyzes dynamics of these sequences and that looks at adversarial sequences and adaptive versus non-adaptive unlearning requests. And I can tell you about that later as well if you're interested. But for now, let's just say we want to forget just this forget set. Okay. Feel free to shout at me if I don't see your hand raised. Great question. What if an example is more than once in D? So, okay, so if it's more than once in the forget set, that's easier to reason about, right? Because you just want this example gone anyway. So you want all copies of it gone, and all copies of it belong in the forget set, so life is good, right? If there's a copy of it in the retain set, that's maybe a little more tricky to think about. I think maybe the correct, so if okay, let's follow sort of what I'm saying now, that the ideal approach is retrain from scratch. If you retrain from scratch, you're still gonna know about that example because it's in the retain set. So I would argue that unlearning there is, in fact, maybe, okay, so it perhaps depends on the particularities of the application, because if I need you to remove an image of me, then you would probably put all images of me in the forget set. You would ensure that that's the case. So you would construct a forget set in that case to fulfill my request. So there would be nothing in the retain set. But according to this definition, if there's something in the retain set, then the model is still allowed to know about it. And the question is more nuanced too, because what if there's not an exact copy, but there's something very similar? Then how should you be thinking about these things? And I'll show you in a second a formal definition that maybe helps with reasoning about it. Yes. um, Depends what you mean by solve. You can always retrain from scratch. And so it depends on what your kind of constraints are. But this is the interesting thing about unlearning is we know a solution. You can retrain unless you don't have access to the training set and things like that, additional constraints. But based on the way I've set it up here, you can solve it. The question is, can you solve it quickly? um, but also I will say that for some cases there exists exact solutions, not for neural networks, but for other problems, like for k-means algorithm, for instance, there exist exact unlearning approaches that are closed form and nice, and you can solve it even quickly there. But for neural networks, the only exact unlearning approaches known are retraining, and I'll define more specifically what I mean by exact in a second as well.
Just a small thing. So A is same in both things, but there are hyperparameters, there are some other things.
I love this question. So here A includes all the hyperparameters and things, but this is potentially problematic. So the formal, actually, maybe let me just move to the formal definition. Can I answer your question in like 3 minutes? Because I think a lot of these questions will be easier to answer once we're done setting this up. But for now, let's just say, the goal is to match the model obtained by retrain from scratch. I'll comment about A in a second. And we want to do this in a more efficient way. Okay. So what does this mean exactly? So I'm hinting at the closer that the unlearned model is to the retrained model, the better. But what does closeness between models mean? How do we capture this? How do we measure this? And in fact, to make it a little more precise, we should be talking about closeness over distributions, not two specific models. Because if you are to rerun the algorithm A with, even if you fix the hyperparameters, if you rerun A with a different random seed that controls, let's say, the initialization or the order of many batches, you're going to end up with slightly different model weights as a result of retraining from scratch and unlearning. And so what we're interested in is how close are these distributions? And so how do we measure this? here's a formal definition inspired by differential privacy. So if you know about differential privacy, this is going to look very, very familiar. But this defines epsilon delta unlearning as follows. If we have our data set D and our forget set S like before, which is a subset of D, and a randomized learning algorithm A with a particular set of hyperparameters, let's say this thing is, it can be randomized, but it's a very specific algorithm, then we will call an unlearning algorithm an epsilon delta unlearner with respect to these ingredients, DS and A, if the following two inequalities hold. And the way to think of this is just that this is a particular way of describing how close two distributions are. This is called hockey stick divergence, apparently, and I'm half Canadian, so I was happy to use it. But apparently it's very common in the differential privacy community, and there exist tools for how to measure epsilon and delta according to this definition. But the only thing perhaps that you need to worry about now, or to take away from this, is that if both epsilon and delta are very, very small, then for these two inequalities to be true at the same time, it means that the green thing and the orange thing are very similar to each other. So the green thing and the orange thing are the distributions you would get if you retrained from scratch without the forget set versus you ran unlearning on top of the original model. So if both epsilon and delta are both very small at the same time, the only way for these two inequalities to be true at the same time if unlearning is successful, from this point of view, according to this definition of unlearning matches retraining. So we're going to use this viewpoint. Now, there's many objections to this. Like we put out a little write-up when we launched the competition saying, this is what we define as unlearning. This is how we're going to evaluate it according to this definition. And there was this discussion board on Kaggle. Kaggle is a platform that we ran the competition on. And they were all like, it was really impossible to do any other work rather than just read all these discussions all day. But people were saying, this makes no sense. Why are you constraining? Why do I have to? So I'm trying to build an unlearning algorithm. Why does my unlearning algorithm need to match your specific way of retraining from scratch rather than another way of retraining from scratch? You can consider relaxing this definition to include there exists a way to retrain from scratch, i.e. a set of hyperparameters, such that if you match that, then you're good. But this definition requires something strong, that you match the retraining from scratch that you would have obtained if you applied the particular algorithm. And another, there's many other objections too. Like, why do I need to match anything? Like, if you give me a network of random weights, that would not be considered unlearned according to this definition because it doesn't match the distribution of retraining from scratch. But one could claim that, okay, but random weights don't have information about the forget set. Isn't that okay? So again, many ways to define the problem. This likely should be application dependent. This definition is inspired by privacy. So if an adversary had access to the particular learning algorithm and to the data set and to the trained model, could the adversary tell if your data was unlearned versus it was never trained on in the first place? We want to defend, this definition sort of implies that we want to defend a particular types of attacks that are inspired by differential privacy-like literature. But we can relax the definition in many ways, and that will maybe be useful for many actual problems. Is that answering your question to some extent? So this is probability over the output of running each of these procedures, and the output is a neural network. So these are probabilities over the weight space of models. Good question. And I had not thought of it as Bayesian until now. But yeah, these are probabilities over weight space, over the weight space. And I will talk in a second about how we can actually evaluate according to this definition. This is a different question maybe. I'm realizing I need to really speed up, but I'm not fussed over getting through all the slides. So I'm happy to keep discussing if that works better for folks. But I'll say next quickly that according to this definition, we can think about categorizing methods as being either exact or approximate. So I used the term exact before without defining it. So what exact means is that both epsilon and delta are 0. So those two distributions are exactly the same. If you set both epsilon and delta as being 0, then unlearning and retraining are the same distribution. And for neural networks, the only way that we know how to do this is by retraining from scratch. And this can be done, naively, just retrain everything from scratch, or it can be done in the context of more clever architectures that kind of are designed to isolate the effect of different data points and different weights. So then when an unlearning request arrives, you don't need to retrain everything. You only need to retrain whichever weights were touched by those examples, and you can get speedups. But these architectures also, like in the worst case, can suffer costs similar to retraining from scratch naively, and also might hurt accuracy compared to other types of architectures that don't isolate the effect of different data points from each other. So approximate unlearning is kind of motivated by, okay, can we do it faster? And can we do it with, better accuracy compared to these like very specialized architectures? So approximate unlearning is about reducing the effect of the forget set. We're not going to eliminate it, but we are going to reduce it to some extent that is maybe acceptable. And there's been a lot of work on this that I don't have time to cover today. There's a lot of theory work that looks at different approximate unlearning algorithms for different convex problems and can have guarantees about like empirical risk minimization or maybe about generalization error. And that looks at similarities and differences from differential privacy. And there's a plethora, like a really, really, really large number of approximate methods that don't have any guarantees. They are largely heuristic, but they quote unquote work well. Quotes, because we don't really know how to define success here, but they work well according to some metrics that are used in practice. To give you an intuition for what these heuristic methods might look like, a common approach is called fine-tuning, or sometimes called catastrophic forgetting, of just take your original model. And yeah, I thought that might get a chuckle out of some people here. You just take your model and you fine-tune it on the retain set. So you're hoping that, okay, well, I'm not training on the forget set for a while, so maybe it will be catastrophically forgotten, which is exactly what I want. It's one idea. It's one thing to try. Another idea is to do something more direct and explicit about it. You're gonna take your forget set, compute the loss on it, and then put a -1 in front of your gradient. So you're saying, what would I have done if I wanted to learn it better? This. Okay, let me do the opposite. To remove it, to unlearn it. This can sometimes work if you do it carefully, but most of the time it just ends up destroying your model if you do it too much. And there's, trade-offs with utility. You want to maintain your model's accuracy and so on. Another related idea is we're going to do descent, not ascent. Descent on the forget set, but I'm going to give it a random label. So instead of saying, I'm going to, train on this cat, but say it's a table. And this is one way of forgetting it. I would argue maybe what you're forgetting there is the association between the image and its label rather than the image itself, but this is also something that works well in practice. And then maybe I'll skip over this to kind of save a little bit of time, but we developed a method called Scrub. The acronym is really nice, but we had to cheat a little. So this B comes from the middle of the word here. But I really wanted it to work. And this is another heuristic method. I won't go. Yeah, screw would sound less nice, right? For a number of reasons. Okay. So I'm going to skip over the details here, but it's a teacher-student method. Has a special place in my heart because it's the first paper I wrote with my dad, but I'll spare you that story as well. So the idea, like at a high level, is that the student is initially a copy of the original model, and then it unlearns, heuristically, by obeying the teacher on the retain set, but disobeying it on the forget set. So it selectively distills from the teacher, which is the all-knowing model. It only keeps the things that it's allowed to know about moving forward. And this worked well on at the time we published this at NeurIPS last year. It worked, state of the art on the benchmarks that existed at the time, which are, problematic and give you an incomplete picture of the world. Worked well on several of them at once, but this is very much a heuristic method, has no guarantees. And this is sort of the landscape right now. We have some exact unlearning methods that can guarantee that you fully eliminate the influence because of retraining either everything or parts of the model, but they're expensive in the worst case, and they might require specialized architectures that have poorer accuracy. Approximate unlearning can be faster, although surprisingly some of these methods are still very, very slow. It can have better utility, accuracy, generalization to new tasks, things like that. But there's most of the time no guarantees. So how are we supposed to evaluate this? How should we know if one unlearning method is better than another? There's three main things, at least, that we need to think about when we are talking about evaluation. One is efficiency, of course, otherwise might as well go and retrain. The other is utility. We don't want to damage the accuracy too much. And then forgetting quality, like, did you remove the things that you're supposed to remove? And the first two are easy, right? We can just use standard metrics for them. What about forgetting quality? This is really the tough part. And of course, you need to find a way to combine these, or at least a way to reason about the trade-offs that are acceptable for particular applications and for different methods. So let me tell you a little bit about the competition, and I'll focus in particular on how we designed evaluation for the competition, and in particular for that forgetting quality mysterious blue box in the previous slide. So our setup here was that we have a vision classifier. We use a ResNet 18. We did not do it on my favorite data set, which is CIFAR 10, because, we talked about it, but then my colleagues were like, really? Privacy on CIFAR 10? What is this cat withdrawing its image to protect the cat's privacy? Didn't seem very realistic. So we wanted something that could convince people that this is a real problem. So we use the data set of faces, but it's a simple data set still. It's a 10-way classification of age groups. So you train a classifier that, given someone's face, predicts the age group of that person. And then some users say after the fact, like, oh, I don't know, I don't want my data used for this, please remove it from the model. And the participants were tasked to unlearn the data of the users that requested removal. Okay, so how did we evaluate success here? Efficiency, utility, blah, 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 forgetting quality, what I said before. Let me just show you how we aggregated things, and then I will dive into explaining this fancy MathCal F, which is what we denote forgetting quality by. So the aggregation here is we just take forgetting quality. I'll tell you in the next slide how we compute it. So higher is better for this fancy F thing. And we multiply it with these terms to correct for utility. So each of these correction terms is the ratio of the accuracy of the unlearned model over the retrained model. There's two terms. One is on the retained set and one is on the test set. Why this particular combination? I hope nobody asks this question because I don't know how to answer it. There's many ways you could combine different terms. We tried to find one that's somewhat sensitive. With the baselines that we were running, it would map things to a range that seemed like it would reasonably separate some baselines. But I'm not saying that this is the ground truth way to combine these quantities by any means. So we can talk more about that later. But essentially what this strategy does is that it will penalize an algorithm if it yields, poor accuracy on the retain or the test set compared to retraining from scratch. So you'll pay some penalty if your accuracy is lower than what it should be. But the meat of the thing is, how do you estimate this like fancy F? How do you do that? So remember, this is the definition that we want to use in order to think about what unlearning means and how we should evaluate it. And so what we are going to do is say that, remember, in this definition, the smaller epsilon and delta are, the better in terms of unlearning. So we're going to say fixed delta. We will say that an unlearning algorithm U1 is better than another unlearning algorithm U2 if it has a smaller epsilon for the particular fixed delta. But how are we supposed to compute the epsilon value of a given unlearning algorithm? So the epsilon and delta values, again, to remind you, are talking about how different the distribution of unlearning is compared to the distribution of retraining from scratch, which is sort of the ideal oracle. How can we measure epsilon? So my colleague Peter Kairouz said, we can think about this as playing a game. And he said, imagine flipping a coin and picking between a retrained model and an unlearned model. And then you take the one you picked and you give it to a auditor, let's say, and you don't tell the auditor which one it is. And the auditor's job is to predict, is this sample that I am seeing a sample of the unlearned distribution or the retrained distribution? Okay, so if you do this just once, you're not going to get much information about anything at all. But if you repeat this a large number of times, you can compute the false positive rate and false negative rate of the auditor. So how often is this actually retrained, but it says it's unlearned, and vice versa. And then, is there something that we can tell about how close these distributions are to one another by inspecting the mistakes of this auditor? It turns out, again, thanks to Peter Kairouz and this nice theorem from his ICML paper, that there's actually a precise way for us to compute epsilon given a fixed delta from the false positive and false negative rates of an auditor. So I won't dwell too much on this, but I'll just state sort of the intuition of this theorem. If an unlearning algorithm is epsilon delta unlearning for a specific data set for get set learning algorithm, and we have a sample of either the retrained or the unlearned distribution, the performance of any decision rule that tries to tell where the sample came from is governed by these inequalities. So the intuition here is that if both epsilon and delta are small, there does not exist any decision rule that can tell these distribution apart with false negatives and false positives being small. So no attacker can succeed at telling these apart if epsilon and delta are small enough. And the reason that we like this is that this gives us a way, if we can instantiate a strong decision rule, it gives us a way to compute epsilon by inspecting how often this decision rule fails, or by looking at the false positive and false negative rates, which means that we can operationalize computing epsilon by running attacks that try to tell apart these two distributions. And this particular slide shows a simple example of this, where you have, let's say, orange is unlearned and green is retrained. And the decision rule shown here is a very simple one. It's going to say, everything to the right of my chosen threshold is going to be predicted as unlearned. And everything to the left is going to be predicted as retrained. And we can compute false positive rates and false negative rates of this and plug it into this equation that falls off of the previous theorem in order to compute epsilon. Cool. And this problem is related to what I told you about in one of the starting slides, is related to membership inference attack. If you can tell apart these two distributions, this says something about which data has been used to train the model. Are you doing retrain from scratch, so the forget set was never used? Or are you looking at a sample from unlearning where the forget set was used and then unlearned after the fact? Okay, how are we going to estimate F? Maybe I'll skip over some of this to get to some other parts. Okay, actually, show of hands. Who wants to know all the details about how we run these attacks and put together things? I won't be offended if you don't want to know. You can always look at our paper as well. Okay, maybe I'll skip over some of these details then. Sounds great. Or I'll just zoom through. I'll tell you that we run attacks, something that relates to a question from before. We don't look at outputs. We don't look at weight space here. We don't try to tell apart these distributions in weight space. That's very high dimensional and complicated. We instead look at outputs, and we run a set of attacks to tell apart outputs coming from retrain from scratch or unlearning. If the attacker succeeds, it means these two distributions are easy to tell apart, so unlearning failed. Okay, I will skip over how we do this exactly, but we come up with this fancy F, and then we adjust it to take into account utility to get our final score. Yes? Great question. I skipped too many details. So what we look at is the distribution of outputs coming from either retrained or unlearned when given as input each example in the forget set. So we do it separately for each example in the forget set. And again, there's a lot of design choices that we had to make here. But one thing that we found is that some examples are much harder than others to unlearn, and that the distributions of outputs look very different depending on which example you fed in. And we want to capture this granularity. So we did it per example. We look at the outputs for each example, compute an epsilon value for each example separately. This is what this is showing here. And then aggregate these via a bucketing procedure, blah, 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 to get the final thing. Cool. Was there another question? Okay. So what did people try? A lot of creative ideas were proposed, and my colleague Vincent Dumoulin made a nice figure that summarizes them. This is a truncated version to fit on the slide, but you can see the full version in the paper. A lot of the methods that were submitted can be seen as being comprised of two phases. One that tries to erase stuff, and another one that tries to fix any excess damage to the model due to imperfect attempts at erasing stuff in the first phase. And so many ideas were proposed for each of the phases. For the erasing phase, this was done by either contrastive losses that tried to push the embeddings of the forget examples away from the embeddings of the retain examples, or what else? Like making the distribution of the softmax distribution, so the output distribution on forget examples look uniform. Unclear why that would end up looking like retraining from scratch, but that was something that was used in these in some of the successful methods too, surprisingly. Or some other methods would go and reinitialize some weights, either randomly or informed by masking based on gradients or other information. Other methods would end up adding noise, Gaussian noise, to parameters. Or a successful one ended up pruning 99% of the network, and then doing a little bit of fine tuning. So the repairing stage was also done in many different ways. Like the most common way was just fine tune on the retain set, which, by the way, I call it repair. You can also think of it as doing a little bit of erase due to catastrophic forgetting, just because it's using just the retain set in the fine tuning phase. So it might play a little bit of a dual role, but it's used for repair. What else could be used for repair? Another one that I saw was KL divergence between the outputs of the original model and the retain set versus your current model that you're updating. So maintain your ability to make the same predictions on the retain set as before, and things like that. And we're visualizing here distributions of these like outputs, the distribution of outputs when fed as input 3 different forget set examples. And you see that first place, the one that came in first, which is all the way, the column all the way to the right, is indeed, visually has a better match between the retrain from scratch distribution in orange and the unlearned distribution in blue. On these specific 3 examples anyway, for illustration. Yeah. So these are histograms of these are the 1D histograms of scalar outputs. So you take each row is a different forget set example. So let's say the first row, for example, is the first example in your forget set. So you're going to take this example in your forget set and feed it through the unlearned model. In fact, many unlearned models to get the distribution. So we take look at the softmax vector, find the entry corresponding to the correct class. We take that, and then we do some logit scaling to it to make it look more Gaussian, even though these really don't look Gaussian most of the time. But this is a procedure used in like other types of privacy attacks. They do this logit scaling to the confidence, so the softmax of the correct class. And they have all these sort of different shapes for different examples. But we see that the unlearning algorithm that scored the best in terms of this metric indeed seems to have a better match between these two things. So these are empirical distributions computed using 512 models for each of unlearned and retrained. Yeah. Exactly. So exact same hyperparameters, the only thing that differs is the random seed. So different random initialization, different order of mini batches. And then you go and rerun many times unlearning and retraining in order to get this distribution over the outputs for each example. Exactly. So maybe what the reason you're asking this is that maybe you're thinking, what are you talking about? Isn't this so expensive? Yeah, you're right. I will discuss this in a second. Cool. Are we making progress? What are we doing here? Are these methods better than what we had before? I mean, yes. So here what I did on the left side of this dotted line, I took some state-of-the-art methods from the literature and computed their score according to this. So the F score is this just this like forgetting quality score versus the blue box, the final score, is after having adjusted for utility. And we see that several of these competition methods do improve over the state-of-the-art methods from the literature, which, sounds like great news. But then again, these were tuned specifically for this particular metric on this particular data set, It's maybe not an entirely fair comparison. And some of those things were developed for maybe different different problems, formulations or metrics or whatnot. There's also, many different trade-offs between these in terms of whether you sacrifice retain set accuracy or test set accuracy. Something I wanted to mention quickly is, do these things agree with each other? Do these different algorithms agree with each other about which examples they had a hard time forgetting? There's many things in the forget set. Which ones are actually easier or harder and contribute more to this forget quality being better or worse? So what this big bar plot is showing is for every example in the forget set, there's one bar here. So there was 400 and something examples in the forget set. You have 400 bars. And what this is the sum over 12 different unlearning algorithms, the sum of the epsilon value for that specific example. So the way to think about epsilon values here, given we skipped over some details, is that the larger the epsilon value is, again, the further apart the two distributions were that you wanted to be close. So larger epsilon means worse unlearning on that example. So if a bar is very, very tall, because we're adding here the epsilon values over many algorithms, if a bar is very, very tall, it means that this example had a large epsilon for all of the algorithms. And some of the bars all the way to the right indeed reach get close to the maximum realizable epsilon, or sum of epsilons, which means that many algorithms agree on them, that they are hard. And there's some bars all the way to the left where many algorithms agree that they are easy. For the sum to be small, it means that none of the per algorithm epsilons were too large. So if you missed some of that, all this is saying is some examples are universally easy and some are hard. We also looked at correlations between examples. But I want to mention a more recent work we did in collaboration or led by Kairan Zhao, whose picture you see here, that tries to unpack what makes unlearning hard, actually. And here we are going to study this in terms of a very simple notion of a very simple metric. We call it tug of war because you want to balance different objectives at the same time. And I'll sort of go over this quickly, but what this tug of war thing is measuring is how far are you from retrain from scratch in terms of your accuracy on 3 sets: the forget set, the retain set, and the test set. So to do well in terms of tug of war metric, you need your unlearned accuracy to match the accuracy of retrain from scratch on each of those sets. And what we find, actually, I'll just tell you about one of the findings here, is that the memorization level of the forget set, how memorized the examples were in terms of label memorization, impacts the difficulty of the problem. So intuitively, if the forget set is not very memorized, so if it's low memorized, if you remember the label memorization definition, that means that the examples didn't really impact the model. The model would have made similar predictions on those examples, whether they were included in the training set or not. So then you know, that what that means is, from the perspective of these examples, you are like retrain from scratch. And so your accuracy will also match that of retrain from scratch. And so you will do well in terms of tug of war, even before trying to unlearn anything. The problem is sort of easy. If the models the examples you're trying to unlearn haven't really influenced the model in the first place, you have no work to do in order to remove their influence. And indeed, you see that for low memorized forget sets, tug of war is higher for all different algorithms. And as the memorization level becomes higher, the unlearning is harder. But we found that two algorithms, Saloon and Random Label, that are both based on this principle of random relabeling, they actually have the opposite trend, interestingly. And so we looked into this a little bit, and what ends up happening there is that if the level of memorization is low, you're really better off doing nothing. Like, you don't have to modify your model to do well in terms of this very, very simple metric. But instead, random labeling is going to go and do some very aggressive unlearning, which is actually having the backfiring in this case, and modifying the accuracy on those examples to be much lower than retrain from scratch. Retrain from scratch would generalize to these examples anyway and would have high accuracy, whereas these methods would end up having a low accuracy there. I'll skip over this, but we developed a way to use these insights in order to improve unlearning pipelines. Maybe I'll just give you the punchline. We found that if you take a forget set and you divide it into subparts that are homogeneous with respect to factors that we found matter and affect behaviors. So memorization. Let's take your forget set. If you knew the memorization score of every example, you can group examples in the forget set based on the memorization scores and unlearn each subset separately. And we do this in a sequence. And we find that doing this in a sequence of, separate subset unlearning can actually really help and improve performance. And you can get even more of a boost if you pick the right unlearning algorithm for each subset of the forget set. Okay, but there's many open questions here. By the way, we started a little late. I'm assuming I can have another 10 minutes. 8 minutes. 5 with questions. I'll take it. Okay. So I said some things that are interesting, but they hold true for a very simple metric. Are they also true if you actually evaluate it in a more rigorous way, like the complex thing that I have described that we did in the competition? And let's think about it for a second. If evaluation is so expensive, not only does it slow down research, but maybe you were hinting at this before. Really? You're telling me that approximate unlearning is cheaper than exact unlearning? But before deploying it, you have to go and retrain from scratch, not once, which is what exact unlearning requires, but 512 times to estimate these distributions to make sure that this is okay before you go and deploy it. I mean, that's not very viable in practice. I would argue that, maybe you don't have to do this every time. You can evaluate it once, and then once you know it works, go and deploy it. It's a bit iffy because, you could do that if you had some understanding of how the behaviors of these algorithms change in slightly different circumstances. And our understanding of this is only just evolving now. This is kind of very early days. So we can't really trust that, okay, if I evaluate it in this setting, and I know the epsilon is less than 5, or whatever, some small number, then it's also going to be fine on those other forget sets. We can't really say that for sure. So can we instead find proxies for those computationally expensive metrics? Not easily. So here we look at a metric that's based on accuracy, and we see how it correlates with these more complex metrics, the metric we developed for the competition. And it's not a good proxy. We see that many methods here, the y-axis lower is better. It's the accuracy gap on the forget set between unlearning and retraining. So there's many methods, the colored dots at the bottom, that have the same accuracy gap. So the simple metric would say they're equally good as one another. but they have very different values on the x-axis in terms of this F score that we developed. So this one is no good. But in this recent work we did that Jamie Hayes led, we looked at easy MIA attacks, simple MIA attacks, and how they, what the evaluation of unlearning algorithm is according to those versus very complex and powerful MIAs, membership inference attacks. And we find, if you use the simple MIA, you're going to really overestimate how private your unlearned model is, so that's bad. But I was a little comforted by seeing this, because if you squint a little, at least the ranking between these things is not too different. It's not identical, but maybe there is some useful signal with a computationally efficient thing. There's other considerations that make unlearning difficult, unlearning evaluation difficult. We also found in this work that actually unlearning algorithms can harm the privacy of the retain set, which is very, very bad because we don't want an unlearning algorithm to protect the privacy of the forget set only at the expense of exposing other examples' privacy. So this is something we need to take into consideration. So I'll use my last 6 minutes. No, I'm just kidding. I'll use my last couple minutes to talk about limitations. I talked about all these grandiose goals that we can solve with unlearning at the beginning. I think we need to really establish clear problem formulations. There's limitations to the definition I discussed. It's probably not suited to all these things. We can discuss more of these things later. Another limitation is, what about unlearning? So we put out this paper led by Ilya Shumailov, who came up with the term unlearning, saying, you claim that you've unlearned, you removed this harmful thing, but I can reintroduce it in context. I don't even need to update the weights to relearn the bad thing. So then have you really unlearned it if it's so easily relearned? And we can, ponder about it. Maybe some things are philosophical, but if we want to use unlearning for, policy or for content regulation, then it's not sufficient to remove things from the weights. Even if you removed it perfectly, the model can still act in the bad ways that you tried to unlearn by just relearning to do it in context. There's interesting connections with this community that I want to highlight. We did this work recently with Naz, who's a student at Mila, that I won't go into now, but this is looking at a problem called transfer unlearning, and you can take a look at the paper later if you're interested. This is my last slide, previous to last, but I won't go over it in detail. This just says that folks in continual learning literature have studied how to prevent catastrophic forgetting. Can we use efforts on how to prevent it, how to prevent forgetting, to inform how to induce forgetting? And here I'm showing a specific example of how a particular continual learning paper influenced an unlearning paper directly. And you can look at this example later. I can share the slides. But they use SVD to separate out the retained space from the forget space and project into the space that requires forgetting. This is my last slide. I want us to think about potential new challenges that arise when we try to do lifelong learning and unlearning intertwined. Are there new problems that are emerging here? Can we talk about forward transfer of unlearning? If I unlearn these examples, does it make it easier for me to unlearn another set of examples later? Can we talk about backward interference of unlearning? Does my unlearning of these examples interfere with previous unlearning? Does it cause resurfacing of previous knowledge due to things like privacy onion effect, or the effect that I talked about before, where the retained set privacy is maybe compromised when you unlearn some examples? And how should we evaluate these lifelong systems that try to do all of these things? Can we come up metrics that capture the right trade-offs, capture rapid adaptation, efficiency, forward transfer, but also removal of knowledge according to application-dependent definitions and priorities? And I'll stop there. Thank you.
Thank you so much, Eleni. So we have time for a couple of questions. Okay.
Thanks, Eleni. That was wonderful. So it's great, a very interesting competition. You set that up. And obviously, in doing that, you have to formulate it in a useful way. And one way you've done that is to move from your weight formalism that you had originally into the output space and do things in the output space. But I mean, I guess the question is, have you thrown the baby out with the bathwater there? So, I mean, I can give you an adversarial example. I could take your from scratch data set, train on that, get all the outputs that I would have for my forget data set on that output, and now throw that away and train a new data set, which is just on the forget data set, but with the targeted outputs that you had on your retrain data set. And it will look like it's forgotten by your classifier mechanism, but in reality, you know, I'll be able to tell whether or not any of those individuals were in the data set. And so if I was selected because to be in that data set because there was a really bad credit risk or something, the fact that I'm in there is still apparent. So I wonder, is it, I mean, it's obviously a necessary requirement, but is the sufficiency kind of good enough? And do you have any thoughts about that?
Yeah, that's a great question. I have many thoughts about it. We thought very long and hard about loopholes of this metric. We actually had to change the rules of the competition halfway through because we found a way people could cheat. So because it's not perfect, we need to impose all these constraints for what people are allowed to do. We did not tell them what data sets we were using. They did not have access to the models. They would write code, and then their code would get submitted to a platform, and then that code would get access to the data set and models, but the participants themselves did not know what it was. So we wanted to prevent people from being able to retrain from scratch. So these sorts of pipelines where you do this first and then you train to match the outputs of right. Definitely an attacker that has access to the weights rather than just the outputs could get information still. Depends on how you do unlearning. It's hard to make a general statement, but this definition does allow for things that have not perfectly unlearned from the weights. They just block information from surfacing to the outputs. So this is indeed something that would satisfy this definition, but is maybe problematic. I think there's many possible considerations here. And one potential call for action for the community is when you're developing an unlearning algorithm, tell me what is the threat model of the adversary that you are trying to defend? What assumptions, what information would they have access to? And this sort of defines what sorts of properties you want your algorithm to have. Sometimes it's okay to just block information from surfacing in the outputs. Some models we only have black box access to, and that's good enough, but not always, I agree.
Hi, thank you for the nice presentation. So let's assume that you obtain a theta star model T, that is the optimal model which has already forgotten the forget set. And now if you do a forward pass of the forget set through the theta star T model, will the model have lower prediction entropy? Or maybe there's also another distance metric which actually defines that this was not seen during the training.
Are you asking whether a model with a low prediction, a model that has forgotten something would have low prediction entropy?
For the forget set.
It depends on how you do the forgetting. This definitely can happen. But again, if you accept the definition that we talked about, then it should have whatever prediction entropy you would have if you did retraining from scratch, sort of. So if you end up being very uncertain, so low prediction entropy, I guess, would mean that you're very uncertain about which class to assign this example to, right? If you're very uncertain, this can make it easy for an adversary to say, even if I didn't train on this example, I would still be more certain about its class label. Why is this model so uncertain about it? Something suspicious is going on here. Maybe they ran unlearning. So in this case, this is sort of the reasoning why you want to not over forget. You want to forget just enough so that you look like you never trained on it, but not more than that. Does that make sense?
Thanks a lot for the talk. It was amazing. Just a very short question because I think Chris has one as well. So because it's so expensive, so you run 512. Like, did you try to just approximate the distribution by a Gaussian, where you just use the mean and the curvature to get sort of like a Laplace approximation of the whole thing?
Great question. I will say that the space of things you can try is so large. There's parametric attacks, non-parametric attacks, and whatnot. And it's very, very likely that our particular version is very far from optimal. I'll just start by saying that. We did not try the Gaussian version, but one thing that's very related to that is this sort of state-of-the-art membership inference attack called Lyra, or Lyra, I don't know how to pronounce it. Lyra in Greek is a musical instrument, so I like that version. But it basically estimates a Gaussian for it's not an unlearning thing, sorry, it's a membership inference attack generally. So it estimates a Gaussian for distribution of models trained with the example versus distribution of models trained without the example. And then when you're attacking, you just look at the likelihood under each of those Gaussians. The reason we didn't do that here is that our distributions were really, really not Gaussian. Right, okay. But then you have to deal with these high dimensional distributions. There's always trade-offs. I mean, I would be very interested to work on sort of better attacks. Here we wanted to stick with outputs rather than weights. And there's other issues with weights too, like different weights. You can have networks with different weights that end up behaving very similarly by permuting things and things like that. It's actually not clear that we should be comparing in weight space either. There's at least some nuances to consider there. But we should try.
Thanks for organizing the competition. Some of my students competed in the class I taught last fall. I was excited about the neuroscience stuff at the beginning, and absolutely the brain forgets, and that's an important component, and we as a continual learning community don't think nearly enough about that. On the other hand, I'm not aware of any neural mechanism of intentional forgetting in the brain of specific examples. But I think the kinds of forgetting in the brain could get at some of those things in your little four-way applications thing. Like two examples are inhibition of learn things that no longer you want. Like, for example, if you learn to be, most of these experiments are in animals, they've gotten them to be super scared of a stimulus by electrocuting them. And then basically they unlearn it through, the behaviorally, it looks like they've unlearned it, but really it actually is very similar to the unlearning. It comes back hard if you bring it back. So after they unlearn it. But that's like on terms of the behavior. The other form of unlearning I know about in the brain is, trying to prune representations to make them less biased. So that happens during a certain, it's one of the hypothesized things that happens during REM sleep. I was just wondering if you had any comments about broader in terms of unlearning, not just specific examples, because I mean, I get the privacy kind of thing, I'm kind of suspicious, but I think there's lots of utility for unlearning in general. Just I'm not sure about the exact formulation you have here.
Yes, we could talk for hours about it. The term unlearning is used widely to mean many things. Another type of unlearning is sometimes it's also referred to as concept erasure, but you can remove a concept. I actually have a bit of a rant about this, but I think the definition I showed today should be called untraining, and that thing should be called unlearning. Anyway, we can talk about this for hours, but people have tried to remove entire behaviors by seeing a forget set that has some examples of those behaviors, but not an exhaustive set of the thing that you want to unlearn. There's been work for this for diffusion models. People have looked at using unlearning to reduce generation of nudity in examples. There's been versions in LLMs where people advocate for unlearning as a substitute for RLHF. So they try to do alignment with unlearning by giving just negative examples, so things you don't want to happen, rather than positive examples of things you do want to happen. And the list goes on and on. There's like works to remove even hallucinations I've seen, and all sorts of things. But I think they each deserve a different problem formulation. I chose to talk to you today about a specific one of these. I think we should write down crisply what we mean by each of these variants of unlearning and how to evaluate them, because that will also look very different for each of those problems as well.
All right, thanks again, Ellie. And we have now a coffee break, and later on the poster session only in the first corridor, up later